Professor Ilya Vorotyntsev, Doctor of Science. My lecture today is about the ionic liquids application for membrane separation and catalysis. Hello everyone, and today I'm going to speak about the application of ionic liquids as a designer solvents and some other application. First of all, I would like to thank to Russian Science Foundation to invite me and say hello to the participant of the conference, Lomonosov. And today we speak from the really historical building of the Russian Academy of Science, and behind me is Sergei Botkin, who actually was born 100 years before me. Was really science, let's say, and he was a great medicine, and he invented many things and theory about psychological understanding of the nature of some disease. Okay, let's coming back to my presentation, and first of all I would like to speak about the problem. The problem is what is human being making with the world. Of course, in the case of the coronavirus, we can see decreasing of the industrial stuff, industrial contamination of the earth, but still we have the natural gas processing, petroleum refining, and electricity producing, some fossil fuel plant, which all brings to the atmospheric CO2, carbon dioxide, and some other really dangerous impurity like NOx, nitrogen oxide, and so on and so on. Of course, in that case, when we spoke about some alternative energy stuff like biogas production and so on, since we have the CO2 and some ammonia or H2S as a context on this production. And this is a problem because we are really influencing about the contamination on the climate changes and so on. Of course, some people can argue about the climate change and the influence of CO2 to the climate, but actually we have only 100 years ago that spoke about the Sergei Botkin, who was born just 140 years ago. And we have only 100 years of the precise nodes of the climate. And of course, we have the GCMS gas chromatography analysis from the air, from the ice, which can be taken out from the north or even south pole, and then we can understand what kind of air was in the dinosaur era, for example. But still, if you see for, 50 years ago, for example, the CO2 concentration in the air was 0.3%, and right now it's 0.4. That means we have increasing of CO2. And of course we have to done with this because it's really important for our children and grandsons and some future generation. And concerning to composition of the natural gas or the biogas, there is a point to separate. And the separate is the, let's say, object of my presentation here today. And of course, if you can see on the slide, of course, we have the methane. This is the main important component. We can make some chemical production or just burn and cook, some eggs, for example, in the morning, or even coffee, and or even lunch, because it's lunch time right now. And also the biogas also has some carbon dioxide, some hydrogen sulfide, and ammonia, which have to be actually separated from the gas to promote better heat exchange, for example, and so on. As I told, there is an impurity which have to be separated from the gases. As for separation, there is several approaches, several methodics. Of course, we have spoke about the traditional one, like cryogenic, rectification, distillation, and crystallization, of course, and some absorption processes, and of course, brand new, which actually was born, let's say, in 19th century only, the membrane processes. In that case, that I'm membrane person, the person who are working with the membranes and the membrane science and technology, of course, I have to say a lot of lovely words about the membrane. And actually, we are the membrane, because the cell the human cell, or even whenever cell actually consists from the membrane, which are separate some different fats, different vitamins, different substances in the cell and out of cell. It's really clear and smart membrane of the human body, of the plant, of the animals, and so on. In our case, we spoke about the polymeric membranes, which are synthetic or metallic membranes and so on, made by us, let's say. And concerning absorption and cryogenic methods, which of course have a lot of advantages and big disadvantage, it's concerning to high energy consumption and special equipment. For example, if you want to create some cryogenic rectification column, we need a lot of energy of a lot of liquid nitrogen, which costs a lot. That means operation cost will be quite high. And in that case, cooperation in between absorption and membrane and ionic liquids, which is really smart material. So we're gonna talk a bit later what it is. And this, let's say, interesting cooperation might be brings a lot of advantages for those problems which I spoke before about the separation gases, let's say. And in our case, what is CO2 separation? For example, we have a fossil fuel or even energy plant, and we need to separate the CO2 from this smoke which you can see in from the pipe on the power plant. Of course, the problem is that when you take out the CO2, then you can make some dry CO2. We can see a lot of on the, I don't know, the beach coast or sea coast. When you have ice cream, and all people who are selling ice cream, they use the dry ice, which is the solid CO2. Or even the like on the presentation on the slide, there's the bottle of the Coke. That means there's this brilliant bubble inside its CO2, which are make this all this happens that not throw up. Okay, but the problem is that we have only delay the CO2 evaporation to the air, and this, of course, it's not really, let's say, good for the for the nature in general. But there is the in the picture there is like traditional amine treating by CO2, and first on the right side you have the column which absorb CO2, and the second column which is more cool, and the second column which is more heated a little bit, then evaporate the CO2 to from the solution of amine. Of course, there is a lot of problem which you need to treating amine for a while, and but it's typical and it's everywhere used, and there is some possible stuff for making this process better. By the way, we was in a part of the project who design and create this power plant, the CO2 separation plant from the energy equipment, and this is the actually 30,000 ton per month. This is quite a big production, but this is by by absorption. As for membrane gas separation, in my lab, actually in my two labs in Nizhny State Technical University and Mendeleev University of Chemical Technology of Russia, we are creating both materials and equipment. And this is the really good example when we understand the process, and we create material for the process, direct stuff. And this is kind of the smart approach which we are promote for a while, let's say. As for membrane processes, of course, the membrane is characterized by low energy consumption and low material consumption in comparison with the cryogenic distillation column. And as I told you before, this is quite a big apparatus like 30 meters high, and actually need not one, you have to need 2 columns, and there is a lot of metal, a lot of stainless steel, let's say, yes. And concerning 2 membrane, you need only 1 box with the membranes, and of course there is less materials there inside. And the problem with the absorption, with the cryogenic or rectification column, for every part you need to calculate the apparatus. For every product, for every new process, you need to change the diameter, the height, and the equivalent theoretical separation plant from the chemical engineering. Okay, as for ionic liquids, this is really also interesting materials which consist from cation and anion. In Russian literature it calls polyelectrolyte or electrolytes, but there is no solvent inside. There are only cations and anions. And in that case, there is a lot of possibilities for using them as a solvents, as a catalysis, and I will give some example in the end of my talk. And also there is the really nice separation technique as well. The key point of ionic liquids, for example, as solvents, there is actually no pressure vapor. That means no evaporation, that means no loss of the ionic liquids as a solvent or separation media. And there is, of course, you can save the money, which is more important for the economical stuff, on the business people, for chemical engineer, no lose the liquids, no lose the material. And that means if it's not evaporate, that means you can use whenever you want. I mean, from a toxic point of view. Of course, you know what's the difference between chefs, which can night smart, I don't know, dish in the restaurant, and chemist. Yes, actually we all do some chemicals, some experiments, but chemists never lick a spoon. In that case, you also never have to lick the ionic liquids, because some of them are toxic and very toxic. But there is, in that case, there is no vapor pressure. That means you can use these toxic materials like a glass of water, but they never evaporate, and then can touch you, they can beat you, and no influence. But not lick a spoon and don't drink at all. But other side of the ionic liquids, right now we have, for example, selenium ionic liquids. They are totally green. Of course, in principle, you can lick the spoon which are put in the selenium ionic liquids, but of course, try to not to do, because you never know where this spoon came from. And concerning my talk about the CO2 or acid gas separation, for ionic liquids, you can use the 2 options, the physical sorption and chemosorption. Of course, the chemosorption is the, let's say, discussing, because the chemical reaction is usually, it is new bond appearance and the old bonds disappearing. And in chemical sorption, there might be some problems about the desorption of CO2 from separation media. And physical sorption is easy. The CO2 can go in ionic liquids, I mean absorb, and can go out, desorb. This, let's say, interesting stuff. And in that case, that ionic liquids, this consist from cation and anion. Concerning acid gas separation like CO2 or H2S, we spoke about more influence of anion to the processes. This is the basic. Of course, you can see a lot of nice review articles. One of them, presenting on the slide, was published 5 years ago in Chemical Reviews. And one of my, let's say, lovely parts of the ionic liquids, you can calculate a lot with them. And of course, as I told in my lab, we are making some material science and chemical engineering, but we also do love modeling as well. And there is the article from the Iranian, let's say, colleagues, was published in Ionic journal in 2013 and was really nice. First is colorful, yes, and chemistry is colorful, and there is a lot of chemical reaction which are colorful. And here's this picture is also colorful. That means you can easily understand what you want. And as you can see precisely on the, you can actually make a pause on your broadcast and calculate how many ionic liquids here. But my guess it's more than 300, let's say, the different cations and different anions, like a small table of multiplication, yes, or even periodic table, yes. But my guess and what we are done in the future work, which I show you right now in a few seconds, we take the average numbers. In that case, or a little bit more than average. In that case, the idea was the CO2 or H2S have to go inside the ionic liquids, that means absorption process, and also can go out the same easily from them. And this is the point why we use the average numbers of absorption ability of the particular different ionic liquids with different cations and anions. Of course, you can see from those numbers, which are those colors actually, but colors means numbers here, which are anions are better influenced, better sorbed, and which are don't, and so on. And this is the, let's say, basement, and there is a nice example to calculate something, to answer, and this, let's say, the minutes of small devices for PhD students. When on the PhD defense or some presentation, some people ask why you choose this object. Of course, you choose because you have this in your lab, or your boss told you, let's take this one and work all this stuff. But other side, you can always tell, we calculate and we think that this might better than others. That's the point. And this is a good example why we use those and those. Of course, we have what we have in our lab and we can choose. But the calculation is the one of the example how to answer the questions. And my first project, which was supported by Russian Science Foundation in 2015, sorry, it was quite long ago, but it was really interesting, and we start with working with ionic liquids. In those time, actually, we have not much experience of working this, and I called to several friend of mine, professors from Portuguese, from Lisbon University, and we try to organize some work together how to use this. But the simple approach, or the simplest approach, how to create the membrane with ionic liquids, it's supported ionic liquid membrane. That means you vacuumize the porous support, then you put the ionic liquids inside, and then you get easily in the several hours, because you have to pump out all air from all pores from the support. Then you get nice membrane, and this is how to look the equipment to create this supported ionic liquids membranes. But we use support which are totally produced in Russia, in Vladimir, in polymer synthesis, which still allowed. And we use, actually, one more advice to the younger generation. They really important in your scientific work to, if you see some trends, to stabilize much more parameters and try to change one of two of them, and to easily understand the nature of the things which you are investigation, let's say. In our case, we use the different materials which were hydrophilic and hydrophobic, and with the same level of porosity, around 80–85%, and with different pore size. And these are brings us a lot of the information about the free surface energy of the polymeric materials, which you can see from the table here. And then we easily calculate this quite simple experiment for the contact angle measurement, and they use Laplace equation. You can easily calculate the capillary pressure. That means the pressure which you use, which you pressurize your membrane, that all ionic liquids can leak out from the membrane. That means the stability of the membrane. Of course, these great numbers which we obtain for 50 nanometers membrane, each about 40-50 bars, it's really nice result, because the real operation condition, it's like around such numbers, about 40 bars. But the problem is, and right now I told what I told here, this the capillary pressure. This, of course, we calculate in these numbers. Yes, and these brings us, let's say, an example for thermodynamic stabilized condition, thermodynamic equilibrium condition. Of course, in the real operation condition, when your pressure might be a little bit different, of course, the numbers can be lower, or you have to save, let's say, safe area for non-leaking membrane from them. And then for those numbers which are porosity with 80-85%, we uptake almost 100% of uptake. That means we have 5 gram membranes, 5 gram porous support, and means it could possibly take around 5 grams ionic liquids inside. And on this scanning electron microscopy picture of the top surface of the membrane, you can see the porous support, and then it's totally covered by the ionic liquids. And of course, we can see what's the difference of the ionic liquids can be into the porous support. Today or this morning, when I look on these slides, I also think about why actually, this is a really nice question. Right now I have no answer. Why we have such different numbers? For example, uptake for membranes with smaller pore size are smaller than for bigger pore size. For example, the porosity is the same, but that means not all pores are covered or filled in by ionic liquids, or even you can vacuumizing really nice the all small pores. That's things for the thinking about this in some nearest future. And then when we uptake all these materials, we make the Henry low constant measurements. Actually, this rather simple equipment, but we have quite expensive the vacuum pump, which can vacuumize the sample 10⁻⁴, -5 millibars. And then we have the number 6, and also, yes, the number 6 and number 5, the really certain pressure gauge, also which costs a lot because the accuracy is really high. If you have higher accuracy, you have the better numbers in the case of thermodynamic accuracy. And of course, from this table, you can compare it with our Iranian colleagues' calculation, and you can see we are really close to the calculation numbers actually. And then we easily can make the permeability measurements. What is the permeability, and check the separation ability of the membrane. This is also quite simple equipment. When I work in Lisbon University, in Professor Jean-Paul Crespa, they show me this really simple equipment. we have upper side and down side of and which chambers which are separated by the membrane, and then you put the gas area in the both side, and then vacuumizing a little bit till atmospheric pressure, and then you just wait and obtain the numbers really easily. Actually, in that case, when I brings, of course, with the permission of my Portuguese colleagues, this equipment to my lab, when we making this happens, we call this particular equipment like Portuguese girl, because it's really simple to operate and really easy get your feedback what is the good materials or not really good materials. This kind of joke. And then this is the material permeability measurements for different gases, for pure gases actually, nitrogen, methane, hydrogen sulfide, and of course carbon dioxide. All data was published in 2017 in separation purification, and was actually nice result, and we can see the influence of the pore size and the ionic liquids uptake and all this stuff, and was really interesting, and there is some trends and so on. And of course we take the best one, the best materials which we obtained, and use for the further investigation. Also we can see from the in the membrane science we have like one stuff we call the Robson plot. It's ideal selectivity with permeability, and this is the Robson line, or upper bond line. They brings the best materials which are obtained by the scientists in the world right now. Till 2000 there were several upper bonds. From every year it's go up and up, because usually in the membrane there is also trade-off between the selectivity or even permeability. If those materials which are permeable, which means very productive, they are usually low selective, and those materials who high selective, they usually low production. In our case, if I told you before that we try to use the average numbers, actually we use the average numbers for selectivity and productivity, which actually are quite good. And this is the ideal selectivity. The numbers for some of the materials are really high, about 100, which is really good. And of course, we take the goal of the project. And also we want to understand what is the difference on how to all this stuff are influenced with the temperature as well, because in some processes the temperature might be high. For example, when you have the fossil fuel separation CO2 from the combustion gases, the temperature is quite high. Of course, it's after combustion. There is some NOx reduction, and the temperature a little bit go down, but still the influence of the temperature on the membrane is really important, and we can see from the pictures that of course with the increase in temperature the permeability a little go down, and selectivity a little bit up, and that means you can find the ideal temperature interval for making your process good. Okay, and this was concerning to the single gas or pure gas permeability, and of course many scientists and of course the chemical engineers are interesting not on the pure gases, they are interested in the reality. What is reality? And of course the first step from the membrane science to the reality, to separation real project, real object, let's say, it's use the gas mixture, like modeling gas mixture, when you make this composition by yourself in your lab and so on. And of course, when you have the gas mixture, you need to understand what is composition. Of course, you can use GC, I mean gas chromatography, to analyze the composition. It's quite easy, simple technique. But when you understand, when you have to understand the permeation, and of course, in some cases, the permeation process are quite fast, you can see the the kinetic of the processes. Of course, it's better to use not GC or GC with mass spectrometry, which have the faster feedback from the equipment. And we try to use this GC, which are for analyzing the permeate, that means the permeate composition. Those gas which go through the membrane, and then we can analyze what's going on in these separation processes. As for materials, we also use different and brand new ionic liquids, which can be synthesized in our lab and then using in the experiments, let's say. And here also, what is important for membranologists, sometimes or in many times in many investigations, if you make some new material, you just check, for example, in those equipment which I told you or shown you before, and then you check the numbers, you get the numbers, you quick published, and then okay. But it's really important to understand how long your numbers are stable, and it means the stability evaluations for the membrane science is really important. And of course, the reality of the science, whenever in the world, because you get funded by certain time for 2 years, 3 years, or even 5 years, and sometimes you have no enough time to check all the stability. But if you want to bring from the science, from the lab to the real production or some small operation plant, you need to do the stability test evaluations. Of course, we done some of them, and the result was for some was okay, for some materials wasn't okay, but then we can analyze the composition, because when you operation and we check the operation separation of the gas mixture, which we are also preparing by ourselves, and for this particular experiments we use more or less natural composition. For example, methane with or 15% of CO2 in methane, or even 5% hydrogen sulfide in methane, because this is the, let's say, natural composition. For example, the natural gas which are harvesting in Siberia, for example, they get some sulfur, and actually this is the number of the sulfur. And actually this is important to separate this acid gases from the natural gas, because before transporting, because we have these big tubes which go through the north or south Europe, yes, and the natural gas inside these tubes or those tubes from Siberia to China, whenever, it should be pure gas, pure methane, or the numbers of acid gas should be really small. Otherwise, we have some, in that case, we have some small amount of the water component. We can obtain some acid, and then we have the influence of corrosion to the pipe in the surface inside the pipe, and it could be damaging. But also we working not only with binary gas mixture, but also with a trinary gas mixture, and there is the 18% of CO2 and around 5% hydrogen sulfide in methane. It means methane there was about 75–76%, as you can see from the slides. And there is the several slides where we compare the single gas permeation and ideal selectivity, and how they influence with different bemene boron fluoride or bemene acetate ionic liquids inside this porous support, and what is the change with the binary mixture, and what's the numbers for the trinary mixture. Of course, it's easy to combine when you have some table, And actually, we also compare our result with some other groups who working with the same materials. Of course, in our case, we have the Russian PVDF membranes might be a little bit different, but for example, from the literature, from Journal Membrane Science 2017 or even Desalination 2009, for example, hydrogen sulfide, we can see, we found in the literature different data. And of course, our data are more close to those article was published in Journal Membrane Science 2017. But why we have these different numbers? That might be water influence on the ionic liquids or water presence in the hydrogen sulfide, because we have to understand what the purity of the tested gases, because it's really important. In that case, the water content in the gas which you are investigation, which permeability measurements, the water contents in the case of ionic liquid separation or supported ionic liquid membranes is really important. And this might be reason why we have different numbers with those published papers, published articles. The same actually with the carbon dioxide, but here not the bigger difference. For example, the same articles in Journal Membrane Science 2017, 12, in our numbers 15. But in the gas mixtures, for the binary mixtures and the trinary mixture, the permeability for selectivity of CO2 to others are, let's say, increasing in the material. But for let's say for the other ionic liquids, it's more stable. That means the different chemosorption might presence, or even the some other mechanism of separation can be realized in those system. And right now in the smart PolyMaT laboratory in the Mendeleev technology, Mendeleev University of Chemical Technology of Russia, we are creating a brand new equipment with the two mass detectors, mass spectrometer. This is the technique also was investigated in our Portuguese colleagues, and actually we are creating right now two equipment, one here in Moscow and another one in the laboratory of the Nobel laureate Konstantin Novoselov in National University of Singapore. And this is kind of the cooperation, but those two equipment are really interesting and really interesting to analyze, because they analyze it really quick and they analyze the different membrane, different gas mixture composition in really quick. And that means we can easily understand the kinetic of the separation process of the gas mixtures, which is really interesting from the fundamental or material science point of view, and also from the chemical engineering science as well, because you need to understand what happens inside your membrane, inside your module, or even inside your materials. But the difference between Singapore equipment and in Moscow equipment, they are working in the plug flow regime or the vacuum regime, and we're gonna compare what is the better and what is the difference of result and so on. Okay, this was the first part of my talk, which are consisting about the, let's say, ionic liquids on the separation media, that means supported ionic liquids membrane. But the second approach is polymeric ionic liquids. Once in 2011, I was the small grant for exchanging for trailing grant to ACS, American Chemical Society national meetings. Actually, this is the really great conference, like Mendeleev Congress, which held every 4 years in Russia, or some European Chemical Congress or some other World Chemical Congress, which also in 3, 4, 5 years. But the ACS make the conference when 5,000 of chemists came to the one city, and you can imagine what happens during the evening or during the night whereas all bars are full of the chemical and the chemist inside, yes, and it's really interesting. And of course there is the nice result presenting there. They also the best equipment in the world. You can see, you can touch on the exhibition. And this was in Denver, Colorado. I was by occasion actually to presentation of the Rich Noble, a professor of Colorado University, and he told about different approach of the polymeric ionic liquids. You can see on the slide, you have the polymeric chain with the cation, and anion is going around the cation. But on the other possibility, you can the polymeric chain with anion and the polymeric chain with cation, and take all together like a sandwich or like stuff like that. And then you can opposite the polymer chain with anions and the cations walking around, let's say. And this is really interesting. And since 2011, I desired to make such materials. And 3 years ago, it was 4 years ago, we approaching the second project to the Russian Science Foundation, and thank you for Russian Science Foundation to support them. And we right now finishing this really actually quite hard, because there is a lot of problems we face with them. But idea was really interesting. We have the polymeric chain with the cation implemented in the polymer chain, and we try to put the different anions there and different cations, and how to obtain the different membranes for separation CO2 and H2S as well. This is the idea how to obtain actually 16 materials. And first we obtain easier monomeric ionic liquids with a chlorine anion, and then with the anion exchange with lithium salts with different anions, we obtained 4 other materials with different cations. And then we have polymerized them, and then we decided to, during the polymerization process, to add some ionic liquids, just 3 ionic liquids, and we obtain actually the composite membrane, composite materials, composite membranes, and there is some advantages for those stuff, because you can combination of facilitated transport mechanism and solution diffusion mechanism, because the ionic liquids are providing this facilitated transport, will then take molecule of CO2 or hydrogen sulfide and go through the membrane. And the polymeric support is realized solution diffusion, with the CO2 dissolved in the membrane, the polymer, and then diffused through them to the low pressure compartment when dissolved in there. And actually the result was okay. We obtained, you can see here on the picture, we obtained 100 nanometers selective layer, which actually quite not so small, but still it's working. And we obtain highly permeate membrane on the composite membrane of these polymeric ionic liquids on the polymer support. And of course, everybody told right now about some renewable materials and so on, because the chemistry is killing the world and so on. And we also even participate in this kind of work. We work with chitosan, chitosan is a biopolymers, look like cellulose, which small difference with amine group, which might be selective for CO2 actually. And then we try to combine these biodegradable materials with the monomers, acrylonitrile or styrene, and obtained ionic liquids, of course, who are responsible for better CO2 separation. And we obtain actually graft copolymer and block copolymer. And then we add three ionic liquids, obtained actually 16 materials. Oh my gosh, that's the same number, 16, like in the previous project as well. But we are checking these materials, and you can see this atomic force microscopy surface pictures. Materials are different, and you can see the size of the anion can influence of the materials there, and also it influence of the permeability and separation properties of the materials as well. Some of materials was non-permeable, and some was okay permeable, some was nice permeable, and actually we obtain this result, which was also in the middle region of the Robson plot of the selectivity and the permeability. And the next approach, also when you just use ionic liquids as well as it is, just put on the polymeric membrane. We call these processes membrane-assisted gas absorption. If you can read only the first letters of those 4 words, you can see it was MAGA. That means some kind of magic process, and we have a lot of joke about this magic and so on. Before we call this process absorption preparation, but people who working with the preparation told that it's not actually preparation because you have the gas solution, but from the physical chemistry point of view there is no difference between how to obtain the solution, yes. But anyway, right now we call it membrane-assisted gas absorption, and here we can easily change different absorbents, which are ionic liquids or solution of amine with ionic liquids, and also we can use the same mass exchange apparatus, and you put the different ionic liquids, put the different absorbent, and actually it's really or even totally change the properties of the separation. Here we use monoethanol amine with different ionic liquids and different composition of the different gas mixture to separate, to experiment, to understand what this is separation. And as I told you before, or right now actually, we have now this quick responsible mass spectrometer, and we use the GC with different quite hard, and this is quite long response for separation H2S or CO2 from methane and so on. But still, we obtained nice result in comparison with the just membrane gas separation. We can see the better result for this, let's say, integrated processes with absorption and membrane separation. For example, if you use, if I came back for a few slides back, if you compare from the traditional absorption-desorption processes, you have the two columns. First column in you absorb the CO2, and the second column have to be heat up, and then you have desorb. In our case, we have only mass exchange apparatus. By bubbling the mixture through the absorbent, we solute the CO2 and the methane, which has no ability of absorption ability, to this absorbent go pumping out or go out by pressure, and this absorbed CO2 go through the membrane because of the pressure difference, because of course here you need to driving force, and in our case the pressure difference or partial pressure change And this is the easy idea which we implement in this experimental setup actually. And we obtained the nice result which are better for in comparison with the gas separation. The article was just published actually in the separation purification journal, and this actually work with gas mixture with different composition. The second, the next example of integrated processes, which actually there is not much ionic liquid, but still interesting. It might be ionic liquids, for example. Here there was also idea to implement in the one mass exchange apparatus three physical chemical separation processes: gas hydrate crystallization, absorption, membrane separation, and this it might be interesting for CO2 separation, methane, and other separation rare materials like xenon, for example, which are really interesting gas for anesthetic stuff, especially for children or people who have some heart disease and so on and so on. But the price of the xenon is quite high, and in this approach can be decreased the price of the xenon on the actual market. We have the real apparatus. Actually, this is also part of the project supported by Russian Science Foundation, and there was nice result. We can easily separate the modeling gas mixture here. And if you remember the topic of my talk about the membrane and the catalysis, and actually this idea was really attractive me for many years, actually almost 20 years, when once I walk in the forest with my father, who actually also professor, and spoke about the idea to separate in the synthesis point. That means, right now all synthesis or synthesis in human body or whenever body might be realized mostly with catalysis. And if you put the catalysis in the membrane, that means you can realize almost like Leonardo da Vinci told, you can mimicking. That means you can in the human world or technological world, you can copying the idea of the nature. And this is the several examples how we can do this, use the membranes in the catalytic processes for separation products from the reaction area. That means we always influenced and we always push the thermodynamical stuff to equilibrium to making the products constantly. This is really brilliant idea, and there is not much actually example, but the numbers of the example it's really enlarging. And from my scientific understanding, the catalysis right now is the top of in the chemistry. For example, the impact factor of the catalysis related journals are really increasing twice in several years. And the membrane also might be helpful for the catalysis, and that is why we are making our next proposal for the Russian Science Foundation project about the combining membrane and catalysis. And this is the several approach how to people realize this stuff for the metallic membranes, some polymeric membranes, for the hollow fiber membranes with some metal inside, which can be catalysis inside the membrane, and the membrane is working, they work for separation, and really interesting. And concerning to the problem which I told in very beginning of my talk about the CO2 separation from the methane or some combustion gases there, we can easily take the CO2 from the gas flow and react and to change the CO2 to the some product. And actually this is the goal of all these ideas, to convert the CO2 to the other product, which are possibly to decrease the human being impact of the nature. And this is all what I want to tell you today, and thank you for listening to me, and thank you for Russian Science Foundation for inviting me here in this nice building. Actually, you can imagine, you don't see, but actually the stuff here is really nice. And thank you for your attention, and I guess we have some time for the questions here.